Buenas tardes, les damos la bienvenida nuevamente a los seminarios institucionales del Instituto de Geofísica. Después de 7 meses reanudamos esta importante tarea académica de nuestra institución. El día de hoy, para reanudar estos seminarios, nos acompaña el profesor Georgios Nicolau de Southwest University, Texas University, para hablarnos sobre el diseño, simulación y calibración de los instrumentos de anatomía de plasma. Entonces, voy a darle la palabra a la doctora Diana Rojas, quien se va a encargar de introducir a nuestro invitado y de moderar el seminario. Entonces, por favor, doctora Rojas.
Ok, muy bien. Buenos días a todos. El día de hoy es un gusto para mí presentar al conferencista del día de hoy. Él es el doctor Georgios Nicolau. Y brevemente les voy a dar una semblanza sobre su ya extensa carrera, pues ya que él es un investigador muy joven. El doctor Nicolau cursó la licenciatura y maestría en física en la Universidad Nacional y Capodistriana de Atenas, trabajando en estudios del comportamiento termodinámico de los protones del viento solar cerca de la órbita de la Tierra y del flujo de estos en la heliofunda. George es doctor en física por la Universidad de Texas en San Antonio, y su proyecto doctoral lo desarrolló en el Southwest Research Institute, estudiando las propiedades de bulto de los iones en la magnetocola de Júpiter. Dentro de su proyecto, además, participó en numerosos experimentos de laboratorio sobre las propiedades de iones de plasma que pasan a través de hojas de carbón y grafeno, las cuales resultan muy importantes, pues son usadas en los instrumentos de plasma a bordo de las distintas misiones espaciales. El doctor Nicolau trabajó como investigador postdoctoral entre el 2015 y el 2017 en el Swedish Institute of Space Physics en Suecia, donde trabajó en el diseño de espectrómetros de masa dedicados al estudio de composición de magnetosferas, composición de especies. Adicionalmente hizo simulaciones de la respuesta de diferentes espectrómetros de masa en órbita, como los pertenecientes a las misiones Venus Express, Mars Express y Rosetta, y justamente sobre esta última misión él también analizó datos de plasma para describir las distribuciones de iones en la coma del cometa 67P Churyumov-Gerasimenko. Posteriormente, del 2017 al 2020, George hizo una segunda estancia postdoctoral en el Military Space Science Laboratory del University College London, en Reino Unido, donde se enfocó en estudiar los procesos del viento solar y también desarrolló modelos de instrumentos de plasma a bordo, del instrumento de plasma, perdón, a bordo de la misión Solar Orbiter, los cuales serán cruciales para hacer el análisis de los datos por venir de esta misión. Lideró también un estudio sobre clima espacial en el que se caracterizó la respuesta de un monitor típico de clima espacial a la ocurrencia de fenómenos específicos justamente del clima espacial. Hoy día el doctor Nicolau trabaja como investigador en la División de Ciencias e Ingeniería Espacial del Southwest Research Institute, donde desarrolla, por un lado, diseños para nuevos instrumentos de plasma, haciendo uso de simulaciones y de sofisticados experimentos de laboratorio, y adicionalmente continúa trabajando en el análisis de datos de diversas misiones espaciales con el objetivo de investigar las propiedades térmicas y cinéticas de las partículas que conforman los plasmas espaciales. Solo recordar que las preguntas las tomaremos al final. Y so now it's just to say that it's my pleasure to have you here, George. And he's not only a good pal, but also a very enthusiastic ping pong player. So just go ahead and share with us, your knowledge. Welcome.
Thank you very much. And I'll go right into the presentation. And so everybody should be able to see my first slide.
Yep, sure.
Okay, so it's my pleasure to be in this seminar and thank you for attending. So today I'm going to speak to you and share some knowledge about one of my favorite topics, which is the space plasma instrumentation. And I'm just going to break it down to 3 components: the design, the simulation, and the calibration. But you will see that these 3 are actually mixed in a nice blend, because you cannot have a successful instrument with any of these missing. from the soup. So I'm Georgios Nicolaou, and I'm research scientist at Southwest Research Institute in San Antonio, Texas. And I know Diana did really good presentation of me, but I also have my introductory slide. So I was born and raised in Cyprus, in the capital city of Nicosia. And in 2005, I moved in Greece, where I took my first degree in physics. Then I continued as a master's student in the same university in the astronomy, astrophysics, and mechanics sector of the National Kapodistrian University of Athens. In 2011, I make the big step to move to the United States and take my PhD in physics and astronomy. At the same time, I was working as a research assistant at the Southwest Research Institute, the place I'm working right now. But in between, I was doing a postdoc. The first postdoc was in Sweden, in Kiruna, the northernmost city of Sweden. And there I worked in the Swedish Institute of Space Physics, and that's the place I met Diana. Then I did a second postdoc in University College London, and specifically in the Muller Space Science Laboratory of this university. And since last October, I'm back in San Antonio working as a research scientist with a focus on instrument science. My research interests vary from solar wind science to planetary magnetospheric science, cometary plasmas, of course, laboratory experiments. I have also contributions to general projects about plasma thermodynamics, and one project I was co-author investigating the Martian magnetosphere. And as a scientist with focus on plasma instrumentation, I participate in numerous mission proposals. So the topic today is space plasma instrumentation. So you understand that I'm going to speak about instruments we use to measure, detect, and measure plasmas. So what is plasma in the first place? Why we care? Why we really want to know what this plasma is doing? Let me first say that the name plasma came from the Greek word plasma, which means moldable substance. It's something you can give a shape to it. And interestingly, in the Greek language, we use the same word to refer to humans as we're supposed to be created from God, given shape from God. Plasma in the universe consists of highly ionized atoms, so charged particles, either negatively or positively charged ions, and neutrals, electrons, and it should be quasi-neutral if you collect a big sample of it. So macroscopically, it should be quasi-neutral. You will hear many people refer to plasma as the fourth state of the matter because it's definitely not a solid. It's not a fluid nor a gas, although sometimes we may use fluid and gas dynamics to describe some of its properties. And plasma can be found everywhere in the observable universe. So you can understand that because it's everywhere, it's really useful to know what it's doing and what are the properties, but more importantly is because we know it's interacting with planets, it's interacting with satellites, it's interacting with Earth. So here, even humans being here down on the Earth's surface. And there are very interesting mechanisms happening in plasmas, which may have applications many other places. So, for example, the fact that it's interacting with planets, including our planet, is good to know what it's doing if we're going to look for life in other planets or if we want to protect our life here on Earth. So let's go to our neighborhood, our solar system. So we have the sun at the center, and continuously, sun is emitting plasma particles radially outwards. So plasma with high speeds, it's emitted all the time in space. And of course, there is a portion that can face Earth, so it can actually interact with Earth directly. So plasma has the property to be highly conductive. So it's carrying the magnetic fields from the sun. And as those magnetic fields interact with Earth's magnetic field, under some specific conditions, we can have a magnetic reconnection. So field lines from the day side of Earth are opening letting these energetic particles to come through the system. And they go at the night side, stored back here. And through compression, we may have another connection at the night side, pushing and accelerating all these particles along the magnetic field lines, propagating down to lower altitudes, and we can actually eventually interact with the ionosphere. So they can penetrate the ionosphere, creating this impressive light that we all know as the aurora. So impressive aurora sometimes actually highlights very dangerous event, right? So we have high energy, tiny particles that they can penetrate the cabin of aeroplanes, reach the passengers, penetrate their skins, which these will be disastrous because, as we know, these high energy particles may cause cancer. But even if they have higher energies, we can get them down to their surface occasionally. And this can cause, for example, major blackouts because these particles can destroy electric generators. And this is not the first time that we know it happened, right? In Canada in 2003, I think. So major blackout in a cold country like Canada can be disastrous. So again, it's really important to know what this plasma is doing and be able to protect ourselves if we can. So in order to understand the plasma, we design plasma instruments. These instruments, of course, they are not only measuring and detecting plasmas, but they can actually resolve their basic properties, like the density and its variations, the velocity of the plasma and its variations, and the temperature. And these are the basic parameters, the magic ingredient, I would say, that scientists need to do their studies and understand the complicated mechanisms that are happening in space or in the ionosphere. Plasma instruments are often complicated. It takes years to put a typical space plasma instrument together from scratch, passing through the test, the design phase, the calibration, and eventually flying it. And of course, there are a lot of people working on these tasks, and they have to get salaries. So it can be really expensive, not only finding and putting together the hardware, but finding all the people, all the team that's going to work really hard to make a plasma instrument successful. But as I often say, space instruments are our eyes in space. That's the way we should work to understand plasma physics. So when it comes to plasma instruments, it's very important to design them properly. So you don't want to spend a huge amount of time and money, start creating stuff randomly, and eventually find out that they're not going to serve your purpose. So you should always have a science question you want to answer, and find the proper design before you even start building the hardware. And there are ways to do it that I'm going to explain soon. But designing the instrument, it's not the entire story. Maybe it's not even half the story. It's very important to calibrate the instrument before you fly it. Calibrate means decode the measurement, right? So you put it in the laboratory, you shoot known plasma to it, and then you see the measurement. So then you can match the measurement with the actual plasma that reach your instrument. That's how you can later understand the measurements taken in space. It's like you get an image with distorted pixels. You should have the map to reshuffle the pixels to get a meaningful picture. So calibration is something like that. So again, if you don't calibrate your instrument, we're still blind. So let's go and see some cool designs of typical plasma instruments. So I'm going to refer to the plasma instrument category that is called the Electrostatic Analyzer. So, and here I use one example, the example of solar wind around Pluto, or for short, SWAP instrument on NASA's New Horizon. This instrument is designed to detect and measure basic properties of plasma ions, actually solar wind ions, that interact with Pluto's environment. So the instrument looks like that. It's like a cylinder, and this silver region around this disk is the aperture. So the particles can enter the instrument to get detected from this region here, around this disk. Let me now make, so from top to bottom, to give you an idea of the size, it's around 20-25 centimeters from top to bottom. So let me now take a cut through this instrument and make the 2D diagram to explain the measurement principle. So you see the positively charged particle will come from the left in this case. And here in the aperture, we have the retarding potential analyzer. It's not really important for the scope of this talk, but since it's there, let me just say. So you can apply a potential difference between these two grids, and then the particles that they don't have enough energy per charge energy to overcome this voltage difference, they will get deflected and get rejected from the instrument. While that they have enough energy, will overcome the potential barrier and continue through the instrument. Now, when they enter this region, they are about to enter the electrostatic analyzer, which is two homocentric, partially spherical shells. This is the inner electrostatic analyzer dome, and this is the outer electrostatic analyzer dome, right? So now if we apply a specific voltage difference between these two domes, we can bend the particle trajectories, and if the particle has a specific energy per charge, can make it all the way through the electrostatic analyzer and continue straight to the detection area. So here we have a detector that will tell us, I record 1, 2, 3, 200 particles. So those that they make it through. So specific voltage difference makes a specific energy per charge to get detected. So you understand, if I scan now in consecutive steps, if I start changing the voltage difference between the inner and outer dome, I can create the energy spectrum of the particles, because I'm going to get the number of particles with specific energy per charge, and I will scan through all the possible steps I can. Let me explain a bit better the principle with some math, because we all love maths, right? So we have the voltage difference, as I said, in a simplistic shape of electrostatic analyzer. The right energy per charge makes it through. If your energy is higher, the bending will not be sufficient to make you go through, but instead you're going to hit the outer wall. Now, if your energy per charge is a bit lower, then bending will be too much and you're going to hit the inner wall. So what is creating the force that makes the particle, the charged particle, to be bended like that? Well, is the centrifugal force, which is the mass, speed square over the radius. Here, I refer to the radius of this central path, the path between the domes, from the center of the circle, right? So this centrifugal force is equivalent to the electrostatic force we're applying when we put a voltage difference between these shells. So if I go here, you see that the distance between the two shells is the difference of the radiuses, and the force I can, the electrostatic force is the charge of the particle, the voltage difference over the distance between the domes where I'm applying the voltages. So now, solving for the voltage difference, I can show that specific delta V corresponds to specific energy per charge, and the K factor is what we call the analyzer constant. Yes, it's constant, and it depends only on the instrument's geometry, specifically the radius of the curvature here and the distance between the domes. Now, in a more advanced design, you can combine electrostatic analyzer with some aperture deflectors. These aperture deflectors are just metallic pieces placed in front of the instrument's aperture. So here and here. Now, if I apply a voltage difference here, not only the electrostatic analyzer, but also in the aperture deflector, then I can bend particle trajectories that they can make it through the instrument. So specific voltage difference here selects specific trajectory in the elevation direction. So scanning through voltages here, I scan through the elevation direction of the particles. So this design is used, for example, in the electron sensor we have on board Solar Orbiter. So it's measuring electrons. Nothing changed from before. We just flip the voltages to bend now. The particles go through. Here we have, again, the same principle as the electrostatic analyzer shown before. So we select elevation. We select energy per charge. And here on the bottom, I have a plate detector, which is, if I now flip it by 90 degrees and have a view from the top, it looks like that. So you see that it's split in different sectors. Those are called azimuth sectors. So particles that they land here, they have different azimuth angle that the particles land here. So see, for example, that here, electrons coming from the right, they will land on the left of the detector. So somewhere here, for example. If the particles come from the left, they will land on the right of the detector, somewhere here. And imagine that this aperture is actually a disk around the z-axis. So you can get all the azimuth directions by just viewing where the particles are detected on this plate. So if we put the whole story together, I resolve elevation direction with aperture deflectors. I resolve azimuth direction with a position-sensitive plate detector. So I resolve actually the direction of the velocity vector. And by resolving energy per charge in the electrostatic analyzer, I get the velocity vector itself. So I can construct with these measurements the three-dimensional velocity distribution function, which is the key measurement to take all the kinetic properties of the plasma that you need to understand the plasma mechanism. Now, here is another example of even more advanced design. This is the design we use, for example, in Juno, the ion detector in Juno that is resolving particles in the Jovian magnetosphere. So for the Jovian magnetosphere science, it's really important to distinguish between different species. So we don't only to resolve the velocity vector like before, but it's ideally we should be able to resolve oxygen from hydrogen or hydrogen from sulfur and stuff like that. So the top part is the same as before. I know it looks a bit different, it's like a monster here. Don't be scared. It's the same principle. We have the aperture deflectors and the electrostatic analyzer here, but now the difference comes from here and below. So now we don't have the detector here when the electrostatic analyzer ends. Instead, the ions continue straight down, and here they hit a carbon foil. So it's a thin layer of amorphous carbon. And it has the property that as the ion hits the foil, electrons are emitted, which are very tiny and immediately attracted by a potential and detected by a detector somewhere here, which this detector initiates a clock. So it gives a start signal, and there a clock is start running in the system. The ion, after it passes the foil, it continues straight down. And eventually it reaches the position-sensitive detector down here. And as it hits this detector, the clock is stopped, right? So we have one start signal with the help of a foil, and we have a stop signal when the ion ends its flight by hitting the detector. So the difference between the time signatures from here to here can give us the time of flight of the ion in this chamber. But the distance that the ion is traveling here is known. So the ratio of the distance over the time of flight can give us the speed of the ion. But since we know the energy per charge from the electrostatic analyzer and we know the speed, we can solve for mass per charge. So that's how you can create not only the three-dimensional velocity distributions, but you can do it for each species separately. Another way to create a mass analyzer is, instead of having a time of flight after the ESA, the electrostatic analyzer, you can put a magnetic ensemble. So this chamber here, I know is not very clearly, I should use a diagram instead of the 3D model, but I hope the principle will be clear. So here we have permanent magnets that they bend the particle trajectories according to the Lorentz force. And if you put the math down, you will see that the lighter particles will be deflected further away from the symmetry axis of the instrument, which is somewhere here. And heavier ions will land closer to the symmetry axis. Now, the position-sensitive detector can give you the radial distance of the particles, and this can be translated to mass per charge equivalently. So you have a mass spectrometer by using permanent magnets instead of time of flight. So this design is used on for the ion detection on Rosetta spacecraft, so detection of ions around the comet. But it's also used, an identical design is used for detecting ions around the Martian magnetosphere by Mars Express, correspondingly in Venus from Venus Express. And it has some benefits compared to the previous design, but also disadvantage. The benefit is that the efficiency remains constant because there is no foil like it was used before. So these foils with time tend to decrease their efficiency, but the magnets are magnets. They stay there and they perform the same way. But permanent magnets are heavy. So that's the disadvantage. So we saw a few cool designs, right? So we can design the instrument to resolve masses, velocities, and whatever we want. But as I said before, designing the instrument is not even half the story, possibly. Calibration is really important as well. And I'm just going to try to convince you using one example from my personal experience. So when I started my PhD thesis, I took measurements from solar wind around Pluto instrument on board New Horizons, but I analyzed the measurements from the Jovian magnetosphere. So New Horizons did a flyby Jupiter for a gravity assist while it was going to Pluto. So during that time, we turned on the instruments and took some data, and I was trying to analyze them. So initially, I treat my instrument, I modeled the instrument response, and the model was very simple. I treat it as a symmetric disk. So I just simulate the aperture, right? A symmetric disk accepting particles from all around. So in my simple mathematical model, the disk is, it has a symmetry above and below its plane. So I could not predict any difference from flows coming below the aperture plane, from flows, symmetric flows, coming from above the aperture plane. But in the data, we could see that there was a clear difference between symmetric flows above and below the aperture plane. Those correspond to 180 degrees spin angle difference. And you see that B obviously has higher fluxes than A. So we decide that the only way to figure out why the instrument is behaving like that is to go to the laboratory calibration, which was very limited. So we had to combine some advanced modeling using the actual geometry of the instrument, combine for sure the calibration parameters. And that was the time we were able to actually model these asymmetries. So here you have the measurement. So you have an energy spin angle matrix as measured from this instrument. And here you have the model after taking into account the calibration. And you see that the asymmetry is characterized quite well. And that was the only way to to understand where the actual flow of ions is going. So in this publication here, we resolve the motion of the Jovian magneto tail as a response to solar wind. And that will not be possible if we're not going to look at the calibration of the instrument and understand and solve the data and analyze the data properly. Another cool thing you can do with some models is cross-calibration. So you can model instruments and cross-calibrate their responses without the need to go to the lab and take the actual instrument. So one software I use very often is called SimIon. So it's an ion tracing software. So it's you can model your instrument structure in it by using either mathematical expressions for the geometries or take the CAD model of the instrument, and the software will make a grid out of it. Then you can apply the voltages on the instrument components that you will do in real life and shoot particles, simulated particles, and then you will see how these particle beams will propagate through your instrument. This is very important to understand your instrument response in many cases. So look, for example, this picture I have here. So this is the instrument with the mass spectrometer using the magnetic, the permanent magnets assembly, which I showed before. So here you see that I shoot ions of different masses. Here I represent them with different color. So the black ones are the heavier ions, and they land closer to the symmetry axis, while the red ones are the lighter particles, they land further away. Now in my simulation, I know what I'm flying in, and I see the response. So I can, for example, calibrate how the distance from the detector center translates to mass. And I can compare with the actual laboratory calibration. So this is an actual study I did to cross-calibrate some basic features of the ion composition analyzer on board Rosetta. The calibration data we have from the lab were really limited. So, I show them in these three panels here. So in the x-axis, you have the distance from the detector, and the y-axis, you have the flux of particles landed on the detector, and each color corresponds to different mass of particles. And below, you see the corresponding simulation using the ion tracing software. Although the comparison shows that the model is not really perfect, but the positions of the mass peaks are quite well predicted. So we match the calibration data with our model, and that gives us confidence. So we can extend now, we can use the model to interpret data in the entire energy range and mass range from the space of the space measurements, which we don't have available calibration. You have to know that sometimes calibrating the flight instruments can be really time consuming, and we don't have an enormous amount of time to calibrate the full range of the instrument. So we take characteristic data, and then we have to rely on models. So that's how we have to proceed. So as I felt confident about the design and compared well with calibrations, I compare with the laboratory calibrations from the identical designs we have on Mars Express and Venus Express. You see again that the comparison between the lab data on the top and the simulation data on the bottom is maybe not perfect, but still can be quite helpful to interpret measurements. Now let me change environment, leave from a comet, leave from Venus and Mars, and go to a much hotter environment, the Sun. So for the last 1.5 years, I work I'm a part of the Solar Orbiter team. And specifically, I'm analyzing the electron data. So I am in the team that takes first the data and take care of them, find caveats, and find proper ways to analyze them. So Solar Orbiter, let me just first summarize the objectives. It's a mission that is really cool because it's going to go really close to the sun. It's going to reach 0.3 AU distance, which is less than 1/3 of the distance between Earth and the sun. And that's unique because it's carrying cameras. So for the first time, we're going to go that close with cameras, take high resolution pictures, and at the same time, probe the plasma at the location of the spacecraft with our instruments. And our instruments are capable of taking really high time resolution measurements. So we can gonna monitor activities on the surface of the sun and link them to plasma dynamics at the spacecraft. This will help us understand how the solar wind is heated, accelerated, and eventually how it's governing the entire heliosphere. So the electron sensor we have on board is this piece we have here. So there are two electrostatic analyzers with aperture deflectors, and the orthogonal mounting, so this orientation of the two heads, help us to have a full sky coverage. So my part is to model this instrument response and see how well I can analyze the measurements. In other words, I model the measurements of the instrument for known plasma conditions. And then I analyze the simulated measurements in a way I plan to analyze the actual measurements. And then I compare the output of my analysis with the input I used to simulate the observations in the first place. If the input and the output of this model and analysis is very close to each other, it gives me confidence that my analysis method is correct and is not losing any vital information. So here you see that I put a model plasma. So the black dots are the model parameters. So I use plasma of these parameters. I model the measurements for each data point. So here the measurements are shown in terms of the distribution function as a function of energy and elevation angle, and here as a function of energy in the radial distance and a function of the azimuth angle. This is for one head, so the one electrostatic analyzer, and this is for the second electrostatic analyzer. So my analysis demands to convert these distributions to a common reference frame, grid my frame and take the moments or fit the distributions and take the output parameters of the plasma. And then I compare them. The red dot is my output. And you see that, well, the density is not perfect. That's an initial analysis. Now we have improved that. But here the model tells me that because the comparison is good, it means that my analysis and the transformation to the other reference frame doesn't lose any information. And because I have a model, I can also say much more easier why I have discrepancies between the output and the input. So since I get my confidence and know that my analysis will work, I apply it to the real measurements. So you see one of the very first spectrum obtained by Solar Orbiter, and you see the data, and here you see my first attempt to derive parameters of plasma out of it. And the discrepancies of the different methods, I know where they're coming from because I used a model before doing the actual analysis. The magic of the modeling is also that you can propose future designs without spending any money or power to put together a hardware. You can sit on your laptop, model an instrument using an ion tracing software or a numerical model or whatever model you like, and prove in a way that a design you have in mind will resolve the science you want to do. And we have done that in numerous proposals so far. And this is an example here, a proposal to ESA, where I took a current design, put it in the ion tracing software, and start modifying its geometry. So you see the modified geometry on the right. This will change the particle trajectories through the magnetic assembly, and you see that in the non-modified design, which is a flight instrument already, the different masses, they land really close to each other on the detector. So you don't really distinguish what is what. But with the modified design, you see that you get the different masses clearly spread on the position-sensitive detector. So here, your resolution is highly improved. And we wanted in this proposal to resolve nitrogen from oxygen and carbon in the magnetic ionosphere. And we show just by modeling, that's the way we convince ESA that what we have in mind will work. So you can ask for tons of money to build your instrument. But first you have to do this, at least this concept study using models. I'm doing a similar job for IMAP. This is a mission that will fly in a few years. It's a NASA's mission. And one of the first components I simulate to be used on an instrument is this grid. So this grid will cover part of the instrument's aperture to block a big portion of the ions getting into the instrument. That's because the fluxes will be really high. The fluxes from solar wind will be really high, and we want to block the right amount so we don't destroy the instrument electronics. So you have to put that in your simulation, run particles through it, analyze them, and then compare the input and output flux and compare with simple mathematical models, and then you can start complicating things. And let me go to the final part and summarize a few of the experiments we do in the laboratory facilities of Southwest Research Institute. So this is one part of the calibration facilities we have here in San Antonio. You see two chambers, the science chamber and the calibration chamber. So smaller experiments go here and bigger experiments go here. A particle beam is coming from the right of this picture. So a collimated beam will interact with your experiments you put here or here. So as a student, a PhD student working here, I spent a lot of time in this laboratory, sitting in this desk right here, taking measurements in these two monitors right here. And the funny story out of it is that they told me that you're not a real experiment scientist if you don't break anything in the laboratory. And I was graduating, so the day of my graduation was coming, and I still didn't have break anything in the lab, except the last day I broke this telephone here. So I guess that's my contribution to science, the experimental science. Anyway, besides that, we took cool measurements to investigate the properties of ions passing through foils. You remember when I was mentioning the time of flight instruments, that they use carbon foils to detect to emit an electron and give a start signal? What I didn't mention is that when the particle beam is going through the foil, it experiences angular scattering. This is one effect. It's also losing part of its energy and experience also energy struggling. But let's, for example, investigate what happens with the angular scattering. So you understand that this shower of particles that result from the scattering will follow different, so we have different paths from different particles. But in the time of flight principle, we have to measure the time taken from the ion to go straight to the detector. But now we have slightly different paths for different ions, right? So this has a longer path to go. So the time of flight will be different. So this means that when you make a time of flight spectrum, you will not have a distinct narrow peaks in your spectrum, but you'll have a broad peaks because you get ions with different time of flights. Now, if these peaks are really close, they will start overlapping. And eventually, you will not be able to distinguish the start from the stop. So you will not be able to resolve the mass of the ions. So we start investigating, understanding this effect, quantify this effect, and see if there are ways to improve it. And that's what we actually successfully did. So we investigate what happens when you use amorphous carbon foil and what happens when you use a few layer graphene foils, so different structure of carbon. And we show here the scattering angle as a function of the initial energy of the beam that go through the foil. The blue corresponds to carbon, for amorphous carbon foils, and the green and red correspond to graphene foils. And you see that for a useful energy range, for example, here is more clearly, and here, the angular scattering is less when you use graphene foil instead of carbon. That means your time of flight measurement is going to be characterized from narrower peaks, so more distinguishable peaks, meaning better time of flight resolution, meaning better mass resolution. So we believe this is graphene foil should be used in future instrumentation to improve the mass resolution. As I said, there are other effects that are happening to the ions as they pass through foils, and we try to quantify many of those, and we summarize our findings in a series of 5 papers shown here. So I think, okay, and one last thing, this business, especially with the plasma instrumentation, gave me the chance to participate in numerous missions, not only with the data analysis, not only with the calibration, but also for proposing new missions. And I have been all around the world because of this job. So it's a cool and fun business. Thank you very much.
Thanks, George. It has been a really interesting and nice overview of all this matter about the plasma instrumentation. And now we will see if we have some questions on Facebook and on the YouTube channel. Just let me go and check that.
Yes.
But meanwhile, I can ask you, I have some questions. And I mean, of course, you pay the price to become an experimental researcher, and that's quite nice to hear about your adventures. But one thing that I have been thinking about, for instance, the experience I had with Mars Express, it's that an important issue, it was to try to improve the efficiency of the instrument.
Yes.
And I was wondering, now that you have been working with Solar Orbiter, how much can you say that this efficiency have been improved?
Yes, so very interesting. So efficiencies vary with energy of the particles. Usually, that's the first thing I will go and calibrate. If I have the instrument in hands and I want to measure the efficiency, I will investigate how it varies with the energy of the particle. So in the Solar Orbiter, for example, we have MCP measuring the electrons. And we use partially model, partially calibration to get efficiency as a function of energy. Besides the electronic detection efficiency, we have the geometric factor, which means how big is your aperture in specific direction, how many particles you can collect down to the detection area for a specific loop direction and specific energy. And then from those reached the detection, it comes the quantum efficiency. From those reached, how many are actually registered by your detector? And the efficiency may drop with time as well, right? The older the instrument gets, the more efficient may become. In time of flight instruments, the efficiency drops, not the detection, it's the detection efficiency. For example, these carbon foils, they stop emitting so many electrons as the time passes. So the efficiency drops because you have less and less particles to give you the signals you want to detect the particles. So it's a complicated story. There are methods to even do it on flight when you have what we call coincidence measurements. If you have the register of the particles in 2 detectors, you can make some mathematical tricks to calibrate the efficiency, and you can do it every year to see how it dropped, or well, I don't think it's going to increase, but you will see how it dropped, and then you may adjust your voltages. Like the MCP is operating in a specific voltage, you may adjust it a bit to increase the efficiency, to anticipate from other stuff that are causing the drop of the efficiency.
So that's quite interesting, because then even though the instrument gets older and it somehow decreases the efficiency, you can just adjust that the efficiency, because you can model and then you can apply some changes, even
up to a certain point. I will say yes. I have seen it happening in New Horizons. And I think they are discussing plans about that in Solar Orbiter as well. But you cannot keep increasing voltages of the MCP. At some point, they're going to don't take too much voltage, even though they're in vacuum. I suspect there's, and also you don't have unlimited power to give from your power supply.
Yeah, true. So just let me switch to Spanish. Invitar a quienes nos estén siguiendo en Facebook y en YouTube. Pueden también escribir las preguntas en español si así lo desean, y se las podemos traducir al doctor Nicolau. Igualmente, si en este preciso momento no tienen preguntas, pero tienen alguna, se quedan con alguna duda, también la pueden hacer llegar al Facebook de Ciencias Espaciales del Instituto de Geofísica, o aquí mismo en el chat del video que quedará en la red del instituto, para hacer cualquier comentario o pregunta para el doctor Nicolau. So I just invite all the people who is watching us to make her questions, and maybe even in Spanish, and then I will try to translate that to you. But maybe something else that I would like to ask you is about this. In one of your last slides, you present this concept study to modify, to introduce the simulation of the response of the instrument in order to get better results of it. This is the work that you have been doing with the IRF people. Yes. And I saw in your slide that the shape of the electrostatic analyzer, it's a bit different. So it's like more elongated. Is that correct?
Yes, true. So we extended a bit the electrostatic analyzer. We elongated a bit. So we also managed to keep the path of the particles, but make the particles, guide them to enter the magnetic assembly with a higher angle, so closer to the symmetry axis. This is because it gives you a more path as you experience the Lorentz force. So the longer you stay in the magnetic assembly, you allow the Lorentz force to do better the separation. So of course, with that, you're going to lose some of the lighter ions, because they will get completely out of your detection region. But that mission focused on nitrogen, oxygen, and carbon. So, and we actually wanted protons to be out of the way, to not create noise. Usually, when you start playing with the geometry of the instrument, you gain something over something else. If you make, for example, a bigger instrument, you increase the efficiency, because you increase the aperture, for example, so you get more particles in, but you make it much heavier. And we both know that heavy instruments are not the NASA's favorite, or ESA's favorite, or any mission's favorite. And it's good to keep actually the instruments light and as economic and we can. So there are ways to modify stuff, and as I said, always the modifications and the improvements should be focused on the science goal you want to achieve.
Yeah, that's true. That's definitely true. So we have one question from Alex. What's the hardest part of the operation of the instrument?
Oh,
that's a tricky one.
Okay, I don't want to be. Oh, I'm a very optimistic person. So I will say that there are very stressful moments. First of all, when you turn on your instrument for the first time, right? Because you test, you make every possible test in the laboratory. You put it on a vibrator to shake it in order to test if it's going to sustain the rocket launch, the vibrations when the rocket is going to bring it on space, but you never know. So maybe something worked in the lab but didn't work in space. So the first stress is that. Then is understanding the measurements. Make sure that what you actually calibrate, it's matching what is measured. For example, because there are big teams working on these projects, right? So you made data calibration and then there was miscommunication with someone who is uploading the commands on the spacecraft, and some of the operations are confusing. That's another thing that the team should be really careful to resolve if there is any suspicion or something like that. And the fun part for scientists is to understand the data. So sometimes you get, well, often you get the first data and see what is going on, right? And then, especially when you go study something new, you should be happy if this is happening, right? Because it's something new. And yeah, stuff like that. I say there are a lot of moments of agony, great agony, or stress in the worst cases. And the whole procedure can be hard as well, before flight. It's time demanding. I have been into the lab for days not getting any measurement because I didn't know what was wrong. And it could be just a simple cable being misconnected somewhere. So that can be frustrating.
Yeah, and also we know that even though everything is apparently working fine in the design of the instrument, in the lab calibration, and maybe going not so bad with the in-flight calibration, then we have, when we have the raw data, already the raw data, there is this another issue that we have to understand the instrument that you already mentioned in order to really give a physical meaning to the data we have.
Yes, and another thing that I would say, the difference between lab and space. So when you have your instrument in the laboratory, you put it by itself in a chamber with everything being controlled. Well, almost everything. Ideally, everything is controlled. But when you put it on space, next to it there are other instruments. For example, magnetometers. The spacecraft is charging up. And this is very challenging at this moment while I'm working on the electron detection by solar orbiter. The spacecraft potential can be just few volts. So ions will not care. Solar wind ions will not care because they peak at 1,000 EV. But the electrons, their bulk speed, it's of the order of the spacecraft charge, actually much below sometimes. So this will destroy your measurements in the lower energies, right? So you have to really understand, besides your instrument, you have to understand possibly the whole environment, including the spacecraft body. And that can be really, really complicated.
Yeah, that's true. So as one of our colleagues said a few years ago, that this calibration stuff, it's partially imagination. It's quite, actually, it's quite true, because we really need to
yes,
make some really tricky stuff in order to understand.
Yeah, I
both
heard
the
that.
and the data.
I heard that phrase as well. I tend to reduce the imagination as much as I can and not use it.
Yeah, it's the experience and imagination. So
I'm sure the scientific meaning is assumptions.
Yeah, that's true. That's true.
Okay. Then yes.
Yeah. Yeah, great. So thank you very much, George.
Thank you.
To accept this invitation to give this seminar at the Geophysics Institute of the National University. If you want to say final words, please go ahead.
I have to thank you really much. It's always my pleasure to share parts of my knowledge. It will be a bigger pleasure if I get interaction. People can contact me for more questions in private. I should give my email somewhere. And I'm sure if they contact your team, please give my email, and I'm going to be more than glad to answer anything related or not to this science. So again, thank you very much for hosting this. It's really great.
Okay, great. Thank you very much. So now I will switch to Spanish to just say goodbye to all the people who has been watching us. Pues con esto damos por terminado el seminario institucional del día de hoy. Agradecemos al doctor Georgios Nicolau por su presencia y les recordamos que pueden dejar cualquier comentario, pregunta, si quieren ponerse en contacto de manera directa con el doctor Nicolau, pueden contactarme a mí, diana.rc@igeofísica.unam.mx, para hacer el contacto con el doctor Nicolau, o bien directamente, como les mencionaba, tal vez en alguna de las diapositivas del video puedan encontrar el correo del doctor Nicolau. Muchas gracias por su participación y los esperamos hasta el próximo seminario institucional. Hasta luego.